Thank you. Okay. So, as I was saying in the previous lesson, we covered functional groups. Today, we're going to dive one step forward. We learned that functional groups are patterns in which atoms bond to each other. But my next question to you is this. When we look at all these atoms, what kind of bond holds these atoms together? Okay, can I have a quick check. What bonds have you learned before in JH2? Chemistry. Okay, I hear a few metallic, covalent, ionic. What kind of bonds are holding these atoms together? It's covalent, huh? Okay, so primarily in biology, a lot of the bonds we are going to look at are covalent in nature. That's what's holding a lot of these atoms together. Okay, so number one, today we're going to look at covalent bonds. But we're going to look at special kind of covalent bonds. They are called polar covalent bonds. To give you an idea what a polar covalent bond is, I would like to begin with a short demonstration. Yeah, I'd like you all to learn from the different tools that I use in class, because eventually I hope that you'll be able to do the same when you go and represent the school for the science baskets competition. Okay? Okay, this is my box of traveling markers. I bring a lot of stuff inside. Okay? Okay, number one, when we look at covalent bonds, do you remember the definition of what a covalent bond is? When electrons are shared, right? So here I have two hydrogen atoms. Let's say we form a covalent bond. We want them to share electrons. Okay. Here I have two hydrogen atoms covalently bonded to each other, sharing the electrons very equally. Yeah? But not all covalent bonds are born equal. Some are less equal than others. Here, have you all read Animal Farm before? Oh, okay, so you okay what I'm saying? Okay. When do you all read this? Oh, I also studied Animal Farm when I was in lower sec also. Then got, what's the horse name? Boxer, is it? Right, Boxer. He was sent to be made to glue, right? See, I remember this. It's the only thing I remember. Okay. Here I have oxygen and I have hydrogen. Let's say we bond them to each other, covalently bonded. Okay, very quickly, I need you to spot patterns. What functional group is this? Hydroxyl, hydroxyl, I don't really care. Okay, yes, it's a hydroxyl group. Okay, you must be able to spot these patterns fast because they inform you of the kind of properties that they have. Okay, here is a hydroxyl group, covalently bonded to each other, oxygen and hydrogen. They also share electrons, but not quite the same way. Okay, got a bit of difference, right? Yeah. So this is the best way I can try to visualize or make you see how covalent bonds can be a little bit different. What do you observe? It's kind of closer to this oxygen, right? What does it imply? Oxygen, I hear stronger force of attraction of what? Wow, okay, wait for several steps forward. This implies that oxygen seems to be able to hold on to the electrons more. It's like oxygen is attracting electrons to itself. Right? The reality is that when we look at atoms covalently bonded to each other, not all the time will the atoms share electrons equally. A lot of times they share electrons unequally in the sense that one atom kind of pulls electrons towards itself. The atom that pulls the electron towards itself more, we say that it is more electronegative. Okay, so that's one new word I'd like to introduce to you. The word is electronegativity. Okay, electronegativity. The higher the electronegativity, the more it will attract electrons towards itself. The lower it is, the lesser it will attract to itself. Okay, that's the first key idea I'd like to bring across. And that was what your simulation was about. I don't know if you noticed. I'm going to go into the simulation now. for those that have played the simulation, I think you have experienced something along these lines. Is my internet working? If it doesn't load in a while more, I shall not waste your time. I am going to, then I'll move on without the simulation. Come on. Okay, so this simulation provided to you gave you two atoms, just random atoms, A and B. But what you could have done was to play the electronegativity. Okay? They gave you two toggles, one for A, one for B to play around. Okay? Am I? Okay, you are allowed to play and toggle with this. I don't know if you know this, but as you toggle, you have seen this thing surrounding it change. Okay? Earlier on, this demo that I did in front of you, I was playing with the electrons in this way, right? The electrons were kind of just side by side like that. In reality, as you go through more lessons with Mr. Low, you'll learn that electrons don't quite stay in the middle when they share. Actually, they exist as a cloud of electrons that float here and there. Okay? So, let's see if it's ready. I guess not. Okay? If an atom, I'm going to translate this to the whiteboard. What does this look like if I were to translate this into a whiteboard version? Okay? We see over here that oxygen kind of pulls electron to itself. In your CA, they ask you to draw electron density, right? Okay, so imagine now I draw oxygen, hydrogen, this is the covalent bond. I can depict it this way. Okay, this is an electron density cloud. Alright? In this space over here is where you could find all the electrons floating around. But the electrons are drawn more towards oxygen. Okay? So this is what it will look like in 2D. Next, how do you know whether something is more electronegative than another thing, another atom? Yeah? Okay, if you want to, you can Google. Okay, so let me show you. If you were to do a quick Google, you Google electronegativity periodic table. You will find a periodic table with a numerical value to the electronegativities. For example, look over here. Oxygen has an electronegativity of 3.44. Let's compare it to hydrogen. 2.20. Remember, the higher the electronegativity, the more you attract electrons towards itself. So if we pair hydrogen and oxygen, you'll find that oxygen will pull electrons to itself. It's 3.44, 2.20. Okay? In your simulation, you will also see something quite interesting. That your simulation, okay, this one doesn't come with it. Okay? If you were to draw electrons more towards yourself, you'll find that the side, the atom that has electrons more towards itself, will exhibit a partially negative charge. We can represent it with this symbol. It looks like a curly-whirly D. Okay? Delta D. Okay, so this is a curly D and negative. This means that it is partially negative charge. Okay? Because electrons has been drawn towards oxygen, the hydrogen will exhibit a partially positive charge. We call such covalent bonds with an uneven sharing of electrons, a polar covalent bond. Okay? Polar covalent bonds are covalent bonds that have an equal sharing of electrons, and you find that one atom will have a partially positive charge, one partially negative. Yes, Shanice?
Like what way is the symbol for the partially negative? Is that an E?
Oh, it's more like a D. Sorry, it's more like a D. So it's more like a D with a hook on top. Yeah? Okay, it's more like a D with a hook. Okay? Any more? And therefore, on that similar note, okay, what will the other pairings of atoms you find in CA 1.1a look like? Okay, in your worksheet, you have been given C and H, you have been given N and H, S and H, as well as C double bond to O. I would like you now, you can search the internet for this same periodic table with electronegativity. You can insert it into your CA. I'd like you now to try it yourself. Can you draw the electron density of the covalent bonds presented to you, as well as label which atom will be partially negative, which will be partially positive? Okay, and then I'll invite a few of you to the whiteboard to draw your electron density for the covalent bonds. Okay, so we have CH. Later someone will come up to draw for me NH. Okay, then the next person, someone will draw CH. Feel free to discuss with each other, then you can come up more confidence. Then there's NH, and then there was a SH, and then there was a C double bond O. What would the electron densities look like when you pair these atoms up? I'd like you to compare the electronegativities of each atom. Do yourself a favor. Can you write down the electronegativity on the bottom of the atom? For example, carbon is 2.55, hydrogen is 2.55. What is hydrogen? 2.2. Okay? Write it down, then you make the comparisons. Then you decide for yourself how you want to skew the electron density. You want to pull it more towards carbon? You want to pull it more towards hydrogen? Okay, so I'll give you some time now to try out the rest of this particular chapter. Okay, next, can I take you all to be a little bit more proportionate in what you are doing? For example, if you take 2.55 minus 2.20, it is a difference of 0.35, right? If you go and make a difference, go and take a subtraction between all of them, you'll find the differences is quite different, right? So, how you skew your electron density is be proportional. Okay? If the difference is very large, then you expect that, oh yes, I will expect to find a lot around nitrogen. But if the difference is very small, you wouldn't expect to see the same thing between nitrogen and hydrogen, right? Okay? So be proportional in that sense. If not, I walk around everywhere, I see 4 drumsticks. It's no different at all. Okay? I should see some dog biscuit, some drumstick. There should be some difference. It shouldn't all look like the same drumstick. give you up to 205 to complete this. It's our clocks. So, oh no, I'm not stop 2. 105. Yes, Shanice. All the periodic table, all this stuff. So right, yeah, I'm going to let you all know later. Whatever examples you just provided here are typical ones you see. You don't need to know. Next time, right, as long as you see OH, you know that O will be the partially negative. Yeah.
We have to write the numbers.
Oh, you don't. Today is just a beginner level. We learn, then subsequently you don't need to even draw this. Yeah. Wait about a minute more. Question to you is, out of these 4 covalent bonds, which one or which of them are polar in nature? Oh. Okay, what does polar mean? Polar means that you will see a partial positive, partial negative charge on both ends. Okay? So which of these 4 are polar covalent bonds? 4 of them? 3, 2, or 1? Okay. I'm going to invite some of you up. Veronica, will you help me do CH and NH? Thank you. Valentina, can do SH and COO. Could I get your help to just do a quick calculation, the difference between each atom? What's 3.04 minus 2.20? 0. Is it 8 something? And then what's the difference between this one? 0.38, right? And this one is? How many punch? Or the math very good one? You Python very good, right? And what got the difference for me? 84. 64. 84? 7? Okay, then this one? 8, 9. Okay, thank you. Okay, let's have a look. Here we find that between carbon and hydrogen, this is the difference in electronegativity. We find that carbon is the more electronegative one. So electrons will be pulled towards carbon. Make sense? We move on to this one. Nitrogen is the more electronegative one. Electrons should be pulled towards nitrogen. Okay? Sulfur seems to be the more electronegative one, so electrons pulled towards it. Oxygen is the more electronegative one, it is pulled towards it instead. So this one is kind of complete all around. Yeah? Okay, so let's compare. We look at the difference between the two atoms. 0.35, 84, 38, 89. In the, as scientists have agreed, right, that only up to a certain difference in electronegativity, then you will really see the effects of the partially positive charge and the positive negative and positive charge. Okay, only if it's beyond, only if it's more than 0.4 difference, then we will see this charge appearing. Okay, if it's less than 0.4, this charge, right, although present, is quite negligible. There won't be any effect at all. Okay, it's almost like it's not there. Okay, so in other words, even for sulfur and hydrogen, this is quite negligible. Okay, it's less than 0.4. So that means on this whiteboard here, this over here, nitrogen and hydrogen is a polar covalent bond. Carbon and oxygen, this is also a polar covalent bond. Carbon and hydrogen, when you see them bond to each other, we refer to them as non-polar covalent bonds. Sulfur and hydrogen, non-polar covalent bonds. Still follow it? If you do a quick Google, sometimes you may find online that they say S and H together is slightly polar, because this is almost at 0.4. So some sources put them as slightly polar. Okay? But key thing here is that this one is polar, this one is polar in nature. Okay? Yes?
So you said some places you put as slightly polar. So do you put as slightly polar or do you put as non-polar?
You put both are fine. Okay? Okay, then actually just now Shanice also asked, right? you know, if it comes to your worksheets or exams, right, you need to write all this out, you need to calculate the difference, you need to draw the cloud. Okay, I'm going to let you know right now that you don't need to. Okay? The whole purpose of this exercise is to help you appreciate the idea that electrons can be drawn to atoms. At the end of the day, this is the only thing I need you to be able to do. Okay, you see, it's very simple. If I give you N and H, can you just tell me which one is going to be the delta negative, which one is the delta positive? Okay, that's all. Okay, now, if I were to just give you carbon and oxygen next time, double bonded like that, right? Can you offhand just tell me, right, which one is going to be the partially positive end, which is the partially negative end? That's the only skill to pick up. I actually don't need you to draw this thing. Okay? So, that being said, if you want to test yourself very quickly, and we go back to that same molecule, and you were saying there's a phosphate bond. Okay, phosphate group. Just look at this over here. Are there any polar covalent bonds here? Just have a look. Are there any polar covalent bonds? Now that you have this additional length. Have not? Okay, actually I don't know. When you look at phosphate over here, what's the electronegativity? 2.19. Okay, then oxygen is 3.44. So possible? Possible, right? Okay. Anyone else? Possible to have a polar covalent bond here? Possible? Yeah, another one. Anyone else? Yeah? This one over here?
Yeah.
Possible. You see over here, this is actually one carbon, and then there's oxygen over here. Possible also? Okay. So, the key idea here is that you must be able to identify polar covalent bonds. Because then you can tell where these kind of partial charges exist. Then you may be asking, why must I need to know this? Okay, that's the next part of the lesson. Okay? So far so good? Yeah? So, there are two lenses I need you to apply from now onwards in lessons. Number one, can you spot functional groups? Number two, can you spot polar covalent bonds? We keep trying until we are like pros at it. Okay? Now we'll take a short break. We're gonna have some fun. Okay? My box of stuff. No, I said my box of stuff, not Starbucks. Okay. Okay, I'd like you all to be in your pairs, and we're going to try an activity. Jia Qi, do you mind doing with Yi Hui? Yeah?
No, sure.
Okay, yeah. Okay, yeah means you actually mind. Okay, so you said don't mind, right? Okay, so
Yeah.
Jia Qi, right? Okay, I'm going to give each pair one dropper. Each pair, can you now take out a 20-cent coin? Okay, 1, 2, 3, 4. You do the dot just now because I was just saying electron here, don't need to take anything. Just delta negative, because can count negative. Yeah. Okay. And then everyone take each pair take one dropper, and then one 20-cent coin. Some of you show up, take one 50-cent coin. Okay? Can you stand up by your CA 1.1b? What's this activity we're going to play right now? CA 1.1b. Okay? You can find out Google Classroom, transfer it to your OneNote. This is what we're going to play right now. Oh, the instructions say 50 cents. Okay, but poor man, I'm working with 20 cents. Cannot find 50 cents, okay? This activity is simple. Okay? This is what we're going to do. One person will be adding drops of water onto the coin surface. Another person, using a device you have, switch to the slow-mo mode. You record the person adding the water droplets to the surface of the coin. Okay? As you add the droplets, I would like you to pay close attention to what happens. Okay, so what we're going to do now is I'm going to walk around with this cup of water. Okay, and I'd like you to just suck up as much water as you can. Can I? Okay, come. Make it quick, make it quick. Very simple, just suck only. Okay, then you stand by, stand by. Don't do it yet. I'll flag the class off together. Ah, you don't have? Oh, I have passed now. Okay, everyone stand by, don't start yet. Okay, but what you could stand by is one person, you stand by your slow-mo camera. Okay, stand by your slow-mo camera. The other person stand by this point. Okay, make sure your points on the flat surface. Right, anyone has not taken the water? It's okay, you don't need a lot. As long as you suck up as much as you can. Alright, have you gotten water?
Yeah, we got it.
Alright, stand by. Okay, I'd like you to record the video once you flag off. And I'd like you to count how many droplets you managed to add on the point surface. Make it a little bit of a competition, so you can add more droplets. No, in whatever time you have, you can take as long as you want, as short as you want. See how many water droplets you can add on the surface of the coin. But when you record it slow-mo. Ready? Okay, stand by, and go. Need more water now. Once you've taken your video, have a look at your video. You observe anything interesting happening. Water is not wet. Water is not wet. I can make something wet. You see? Just suck up from the table again.
Yeah, I tried to say that, but then like,
Okay. It's very easy. Okay, let me show you my slow-mo video. Then you go and rewatch your own slow-mo video and see if you see this. Okay, here's mine. Okay, slow-mo already. Watch slow-mo. There's a chance it happened to yours. You just need to pay attention. This also using my phone. I never use any special thing. You want to look at your own video? You may have thoughts such as. Okay. Okay, now second round. Would you like to try again? Okay, now you know what you can do. You want to get some more? Yeah. Instagram or not? No. You must advertise bio. Got some discount there, right? You put your yeah, tag me. Tag me, then I will repost and share. Huh? Really? Where is it? Oh, okay. Wow, it's like. You want to do one?
Oh, there we go.
Okay. Sorry, let me pause. Wow. It's not like one blow.
Bigger one.
Like the big one like that?
Like very big one. Oh, even all like this.
Use $1 is it? Oh.
Can you do one dropping?
I don't want video editing. This one, right? Like this one.
Oh my god.
Okay, I'm gonna have to cut your activity soon. Y'all managed to see what I see? Have a you. Hey, okay. After I did this, right? Every time I go coffee shop, drink coffee, right? I also do the same thing, you know. You don't. Of course, I don't bring around a dropper lah. So what I do is that I'll use my spoon, then I'll scoop out a bit of the coffee or the tea, right? Then on the surface of the coffee or tea, I'll like drop. Then I'll like drop. And I'll be filming in slow-mo. I don't know what the people around me thinking, but I'll just keep doing it until I capture. You can also do it on that kind of surface. Yeah? My record. Actually, I don't go for record. I just want to see the ball. Okay, may I get everyone to pass your droppers to the front? Let's try to make sense of what we saw. Why? Can I get everyone to think? Why is the water able to hold itself on the surface of the coin, not just overflow immediately? Why was that droplet able to bounce on the surface a bit before merging with the rest? Why? Okay? Okay, as you are backing up, I'd like you to discuss your partner and then to hear your answers. Yeah? Let's keep the conversation active, fluid and fun. Why? Yeah, I don't want any lazy thinkers here. I want you to think, discuss with your friends. You look like you're staring in blank space. I'm going to call you next. Yeah, Santosh? Well, come by and you're nodding your head humorously in this case. Nice. these are water molecules. Can I zoom in? Okay. Yeah, let me keep out. Okay. What's the red atom? What's the red color atom? Oxygen, can? Okay, the red one is oxygen. What's the 2.1? Nitrogen? Okay, hydrogen, yeah? Okay. So these are many water molecules, can? We want to try to understand what's happening at a small scale. Okay, so these are water molecules. Okay, so why is the water able to hold itself together and not like overflow immediately? The clue lies in what we've just learned. Okay, the clue lies in what we've just learned. Okay, we work as pairs, yeah? Okay, whichever row I call, then you all can work together as a pair to try to answer this. Why? Okay, Han Yu looks like she has a lot to say, along with Anu. Okay, would you like to share where your conversation is at the moment? What do you think is happening? Okay. Okay, Anu, you say again. You said the oxygen is? Go on, yeah? Doing good. So they just what? Keep together, okay. So Anu and Tai Yu has come to the conclusion that, we just learned about polar covalent bonds. Could it be that the oxygens here are partially negative, all the hydrogens are partially positive, and could there be some sort of keep together force between them? And she says specifically between oxygens and hydrogens. I'd like to show you a simulation. This is the internet works. Okay? This simulation you also can find in. Okay. So this is water. Let me switch on the partial charges so you can see the plus and the minus. Now let's slow things down. Now you pay attention to one of the hydrogen or one of the oxygen. Observe what happens. Do you see a pattern in the way they attract each other? They're what? Punch each other. Punch each other. Okay, kind of punch each other. Okay. So actually Anu and Tai Yu kind of hit the jackpot. That's kind of how water molecules are able to interact and hold each other together. True, if we look at a single water molecule, here, oxygen with a 2 hydrogens, we know now, just from looking at this is partially negative, partially positive, partially positive. Alone by itself doesn't quite make any difference. But if I have a second water molecule over here, there is an attractive force between the negative and the positive ends. This attractive force is not a permanent bond. It is not any sharing of electrons. It is not a bond per se. It is more like an attractive force. Like two magnets very close to each other, they can want to attract each other, but they don't share electrons. Okay, you must understand that. We refer to such an attraction as a hydrogen bond. Okay? As a hydrogen bond. Yeah? This attraction between polar covalent bonds, they are hydrogen bonds. Okay? can hydrogen bonds take place between other polar covalent bonds? And okay, let me show you other examples. For example, let's have a nitrogen and a hydrogen. We learned, right, that there's an amino group. If I have a hydroxyl group nearby, could there be hydrogen bond? Can. Okay, between where and where? Okay, here's a negative, here's a positive, here's a positive, here's a negative, here's a negative. Okay, positive, sorry. Where may we find hydrogen bonding? Okay? Sorry? Can you come up and draw where you think you'll find hydrogen bonding? Wait. Okay, usually we depict hydrogen bonding using parallel lines like that. Okay? Not dotted line. Because we use dotted for other kinds of temporary interactions also. Okay? So we like to use this line. Sorry? Try. Everyone also try mentally. Where can these fella and this fella interact with each other via hydrogen bonding? Possible? Any more? Possible? Yeah, any more? Possible, right? Possible. Okay, thank you. Let's give a round of applause, sorry. Yeah, it's okay. Quick thinking, just come out, just try. Okay, we'll learn together. Okay, so hydrogen bonding, please understand that it is not like a covalent bond. There's no electron being shared. It is just an attractive force between each other. Okay? Right now, in your CA 1.1b, oh yes.
You call it partial electronegativity. Why is it only partial?
Okay, why is it only partial? We use the word fully charged more in the scenario of ions. So I'll give you an example. Let's say you have a sodium plus ion that's fully charged. It actually took the electrons away. No, it actually gave the electrons away. Sodium chloride, right? Cl minus. It actually managed to grab the electrons totally to itself. But in a polar covalent bonds, even though a lot of the electrons are drawn towards oxygen, okay, a lot of the electrons are drawn towards oxygen, oxygen never actually truly takes it fully. Okay? It doesn't snatch it away, unlike in ionic bonding. So we say it's partially charged.
So fully charged is only for like ionic.
Correct. Okay? We only refer to something as fully charged when it is in an ionic bond. When they totally, snatch away the electrons. Okay? But in covalent bonds, remember, it is still shared, just unequal sharing. Yes,
I think
it is.
it's like, sometimes partial and then positive and then partial is negative charge. But then if it's bonded with a different one, but like something that was actually a positive charge become a negative charge in a different.
Well, sorry, I don't quite. Oh, are you saying that could this suddenly bond to something else?
Yeah, and then like become like completely different one. Okay, I can't find an example right now, but okay, let's say something is the charge is 1 and 2. But then after that, so 1 is the one which is positive charge, then 2 is the one with negative charge.
Okay.
Then after that, 2 bonds with 3. So 2 becomes the positive. As in yeah.
So let's say this is suddenly less electronegative.
Yes.
Okay, so great point. Polarity can change after reactions. Okay? So if a chemical goes through a chemical reaction, you rearrange the atoms, how they bond with each other, the property of the covalent bond can change. Okay? So polarity can change after reactions. Yeah? Yes? Okay, if there's no hydrogen, is this still called a hydrogen bond? No. Okay? But you will find in biology, a lot of the examples we give you between polar covalent bonds, the attraction, right, always include hydrogen. Okay? So in biology's context, we can refer to them as hydrogen bonds. You find just now even between, okay, just now there was like that, right? Okay? This is considered a hydrogen bond. This is also considered a hydrogen bond. Notice hydrogen is somehow in the picture. Okay? In biology context, you will often find hydrogen to be in the picture. You know why? Because hydrogen is one of the least electronegative atoms. So when it bonds to someone else, right, it tends to be the partially positive one. Yeah, that is usually why hydrogen is involved. Yeah?
Even if you have three, then how do you split the negatives?
If it's three, how you split, is it?
Yeah.
You'll find the electron cloud kind of skewed to depending on who has the most electronegative nature.
Then how do you label the thing?
How you label? That's a good point. We, at least in the bio context, we don't really work with three parties. We can work with just two only. I would suppose if there's three, right? Well, actually, I don't know how we don't play. If there's three, okay, if there's three, I suspect what will happen is that you will take the two that will have the greatest difference. Then you'll just play with the two that has the greatest difference rather than three parties altogether. Okay? Yeah? Can three hydrogens?
No, like in 1, 2, 3 context.
Yeah.
Can the three like hydrogen bond with one even though like just like
Oh, can this hydrogen bond with this? Okay. You will find in later contexts when we learn more about biomolecules, there are certain contexts where molecules can hydrogen bond with itself. Then it causes like a bending, you know. Imagine if my foot can hydrogen bond to my head, right? Then I will like connect. I'm not flexible enough. Okay, then I'll connect in that sense. Okay? So it's possible, but you'll learn later on. Okay? Now inside your CA1.1b, there's one segment I would like you to try. Okay, paste the photo in the space below and annotate it by labeling elements and type of bonds present. Okay, actually, I'm supposed to give you cutouts of tiny water molecules. So here I have cutouts of tiny versions of what I have on the whiteboard for you to rearrange on the table, take a photo and include it into your notes. Okay? But I want to do something more interesting. Could you instead draw 3 water molecules? Okay, just for your own learning. Can you draw inside that space below? I'd like you to draw 3 water molecules in this format. I'd like you to label the ends appropriately. And I'd like you to draw the interaction between 3 water molecules. Okay, so your 3 water molecules that you draw in that space, can you just draw it in this structural format? Don't draw the Mickey Mouse shape. Okay, could you draw this out for me? O bond to H, O bond to H, delta positive, negative. And draw 2 more and depict hydrogen bonding for yourself so that you can refer to it as your own notes. As you continue with that, I'm going to prepare you for activity number 3. I really like cloud, I think so many things. Every care take 2, yeah? Yeah, so can you draw 3 water molecules here and depict hydrogen bond? Yeah, correct. Yeah, but so what we draw is actually a snapshot in time. Yeah. This one. Okay. Yeah. You're right. Because there is no sharing of electrons or giving out of electrons. Just think of it as an attraction. what I will need you to do. You have been given 2 vials. Could you take out the cap, place the cap on the table, both caps on the table, don't spill the water. Your cap, I'd like you to invert it. I'm going to put something inside each cap. Okay? I need someone trustworthy to do this next part. Okay. Help me do it fast, Xiao, help me. Yes, you're trustworthy now. Okay, Xiao's going to do this. She's going to go around distributing 2 spoonfuls of normal sand into one of the lids of the cap. Okay, Alpha on the other side, put into 2 lids. No, 1 lid. Okay, 2 spoonfuls. Okay, I'm going to raise you up. I'm going to distribute this orange sand. This orange sand is a special kind of sand called hydrophobic sand. What does hydrophobic mean? Yeah. You're right. Okay, so actually it needs to be close enough, right? Then you can be quite strong. Yeah. But in this case, theoretically, right, you can. But in real life, right, it's much more like a simulation. You be close enough, then you might. Okay, lah. Theoretical sense, right? You understand. Although Xiao is catching up. Yeah, so everyone should have 2 spoons of hydrophobic sand, 2 spoons of normal sand. Oh, sorry, I spilled everywhere. Do you know what the word hydrophobic means? Can you make a guess based on the word? Yeah, hydrophobic means scared of water. Hydro means water, phobic means yeah. So if you are a teacher phobic person, also don't know. This one look like the sugar that you use, right, when you eat putumayan. You know what putumayan is? Oh, just nice. Hey, before we begin, I would like everyone to make a prediction. We are going on to the next activity. Interactions between non-polar functional groups. Can you spend some time now to predict what will happen when you add a spoonful of normal sand into water and if you add a spoonful of hydrophobic sand into water? I'd like everyone to make a prediction first. Okay, pick up your pens and write your prediction down. Then we will do it together and see what happens. Okay? Thank you, sir. Okay, let's make a prediction. What will happen when you add normal sand into water? What will happen when you add hydrophobic sand into water? Hydrophobic means fear of water. Okay? Once you make your prediction, I'd like you to look up. Then I know you're done. I know you can stand by. looking up? You made your predictions? Okay, once you make your predictions, this is the next step. You will add the sand. I need to be very clear because there's one funny person that did this. I say add the sand and water, right? They added the orange one into the water. They added the same sand, right, into the same vial. Separate, that's why I give you two vials, okay? So orange into one, the normal one into one. Enough? After you add it in, I'd like you to take a photo and include it into your CA 1.1b. Okay, I've given you two spaces. Let's see if your prediction holds true. Ready? Okay, you may add the sand in. Just pour from the lid. Okay, I'd like you to take a photo once you have added the sand in. You want to take video so can this screenshot later? Yeah? Yeah, hello? Hydrophobic means fear of water. So, which one do you think is the hydrophobic sand? Okay, why the orange? This one also has some fluidity. I suspect it is because it's less dense. But you see when I push it, right, you kind of, yeah, it doesn't want to interact with water. Yeah? Give it a push, see what happens. Give it a push. Push some more. Okay. Some of you notice your orange sand floor on the top, right? I would like you to give it a push down. See what happens when you push it down. Go ahead, push it down. Just be there in this picture again. You know what's amazing about this sand, hydrophobic sand? If you try to fish it out again, it will be dry. Okay? If you don't believe me, you try to fish out the orange sand, it will be dry. I don't know how you do that. I don't know how you're going to fish it out, but you can try. It will be dry. You can use your finger, dip it in, then you fish out a bit, it will be dry. Okay, let's wrap this up. I just want to hear your observations. Okay, when you added the normal sand to water, what did you observe? Okay, I hear some words. Number one, you said that you saw the sand sink to the bottom. You have not observed the same thing, or you observed something different? Okay, you saw a big flow at the top. Okay? Anything else? What happened when you added the hydrophobic sand? Sorry, Keller? Okay, Keller said what you observed was that they were stuck together, is it? Okay, where were they stuck together?
Wherever you push it. If you push it down, it will go down and stick together. If you didn't push it, then it will float together at the top.
Okay, so if you didn't push it down, you observe that it will kind of clump together at the top. Then when you give it a push down, then they clump together in the water. Yeah? There seemed to be a clumping effect when it was in the water. Saw that? Let me share with you how hydrophobic sand works. Do you know what's coating this hydrophobic sand? Actually, yes, you saw air bubbles, but actually we sprayed it with a special paint. Okay, we actually sprayed it with a special paint. This paint is made of chemicals that contain a lot of carbon and hydrogen bonds. I don't know if this starting makes sense to you, okay? Carbon and hydrogen bonds, are they polar or non-polar? Have a quick discussion, Carbon and hydrogen bonds, polar or non-polar? Non-polar, right? So we sprayed this sand, the orange one, with non-polar chemicals. We sprayed it with chemicals that have non-polar covalent bonds. What about water? Water is filled with H2O that is polar. You see what's happening here? The reality is this. When you put non-polar with polar, they just don't want to interact with each other. But if you put polar and polar together, you get hydrogen bonding, yeah? But when you put non-polar and polar, they just don't want to interact. You know what oil is made up of? You always see oil just separate from water, right? Oil is made up of a lot of chemicals that contain carbon and hydrogen. Sorry, yeah, Shanice?
If you then non-polar and non-polar, will they have hydrogen bonds?
Okay, now the next question is, between non-polar and non-polar, so let's say you look at two sand grains. One sand grain here and one sand grain here. Shanice's question is there any attractive force between non-polar and non-polar? Who says yes? Who says no? Then my next question to you if you say no, why is it we observe the non-polar sand clump together? If there's no attractive force, why are they clumping together? Right? Okay, give me a think. How are they able to clump together if there is no attractive force between the sand at all? Yeah, they are not polar, there's no partial charge, nothing to attract them to each other. Why are they clumping with each other? Can we solve this mystery? What is causing them to come together? Yeah, I'd like to hear your thoughts. Okay, between Rin and Isabel, what's your discussion? Where is it led to? Okay, so the question was, how is the sand able to come together when there is no attractive force between the non-polar CH? Yes, Isabel, or Rin. Okay, let's listen to Isabel or Rin. Okay, so Isabel thinks perhaps since non-polar and polar repel, when you submerge it underwater, the water surrounding kind of like repels it towards each other. Okay, one view, right? One view. Mia is your? Same view. Okay. Valentina, Jaden? Same view also. You're like Bluetooth hive mind, is it? Wani? Same okay. Actually, you are quite spot on. Okay, I think logically one thing leads to another. How are they able to clump with each other? Not because CH and CH non-polar groups can attract each other. No. They clump together because they are being excluded by the water. Okay? They clump together because they're being excluded by water. Let's say we bunch our class, right? We go overseas right now into a foreign land. We come together because we have the same identity. Right? But actually when you're in Singapore, you feel safe everywhere, you just disperse yourself everywhere. But then when you're in a foreign land, you just want to come together. Right? So this force of attraction, there's a name for it. Okay, we call it hydrophobic interaction. Okay? Hydrophobic interaction. It is that bringing together of all the non-polar groups. But it's a very odd interaction because it doesn't always exist. Notice that it kind of only exists because we mix it with a polar medium. Right? We mix it in water, that's why it exists. It's only because it is in a foreign land, that's why it comes together. What if I take this hydrophobic sand and I put it in a third beaker containing oil? Oil is made up of a lot of chemicals with a carbon-hydrogen bond. It is also non-polar. So I'd like you to think about this. If I take this same hydrophobic sand, I put it in oil, which is also non-polar, what will you observe? Will there be hydrophobic interaction? Okay, so that is the last part of the activity. Will there be hydrophobic interaction? What do you think you observe? Yeah, yes or no? Okay, I'd like you to make a prediction. Once you made a prediction, you can access the YouTube link to see what really happens. I don't want to do it in class because, okay, wait, I'm going to review the answer. Okay, I'll tell you all, after you are done with this, I'll go back to my lab, right? I need to sieve out the sand and just mix it to prepare for the next class. Then the sand you have right now, right, is I just came from 303, right? 1 hour ago I could not take, right? Then I go back to the lab, right? Then I sieve everything out, right? Then I come to this class. So, the oil one, okay, you all predict first, then you all watch the video. Then maybe you'll understand why I didn't provide oil.
I think it's
Okay, what do you think will happen if you throw hydrophobic sand in oil? What do you think? Oil? How the hydrophobic sand? Oh, so that's what you think of hydrophobic sand? That it will push the oil out. So imagine I take this orange sand, right, and transfer it out of the middle. I throw that sand. How do you think you will feel?
because it's not.
Why? Yes, Shanice?
Why are there air bubbles around the sand?
Okay, why the air bubbles? Good question. I suspect the air bubbles snuck in just because, you know, when they don't interact with each other, right? Then the air bubble filled up that space, they didn't interact with each other. I don't quite know what it would look like per se, you know, if something doesn't interact, but this is the best you can visualize. I think the air just managed to find its way in, right? If not, it will be kind of like the sand on top of the water just now. You don't see any air bubble in between, right? I think the air stuck in when you push it down.
Then what about oil? Because oil, right, you know, people put it on like the water, then mosquitoes cannot come because no air.
Yeah.
Then how is the sand gonna go through? Because we cannot bring down any air. Right?
How's the sand gonna what?
How is the sand gonna go inside oil? Because like you see here, there are water bubbles around the
Yeah.
sand. And then the oil won't allow the air bubbles to come in.
Okay.
So how is that gonna work? How's the sand gonna
Okay, so is your question, how is the sand able to go down but the oil doesn't?
How's the sand supposed to go inside the oil?
The oil.
Yeah.
Oh. So are you saying that it will float on top of the oil? Possible? Okay, so whether something floats or not depends on density, right? So let's assume this sand is, hydrophobic sand is denser than oil. If we assume it that to be the case. How do you think it will interact if we put it in oil? Yeah, both are non-polar so far, right? Okay. So I'm going to end off today's lesson. Let's see if we can watch the video. my pen is not working either. This pen, is it? Yeah, it's not working. Okay, so I'm going to show you the video before we end today's lesson. Okay, have you made your predictions? What will happen? Hydrophobic sand in oil. Okay, you hear what he said? It will act like sand in plain water. Okay, let's watch out. Okay, this is hydrophobic sand in water. And this is hydrophobic sand in oil. Okay? Alright, so that's all today. Hydrophobic interaction.
Continue the video and slow down. You only bring it down.
Oh, yeah, actually if I play it, right, you can see it's sprinkling the sand on top. Yeah? And then it slowly rains down. Okay? Okay, so in other words, hydrophobic interaction only exists when you place non-polar things in polar medium. Okay? If you place it in a non-polar medium, actually this doesn't exist. Okay? It is an exclusion force. Okay? Okay, so we covered 4 things today. This is your. Can you help me complete the last activity of CA 1.1b? Okay, the last thing of CA 1.1b is this last part. Interactions between charged functional groups. Okay, that's the last thing of this. And I'd like you to complete it at home. Okay? CA 1.1a, when is a reasonable time for you to submit it via Google Classroom? Today can or not? Okay, so by the end of today, can you submit it to Google Classroom?